The universe was supposed to be empty, silent, dark, but when the James Webb Space Telescope opened its golden eye and stared back to the beginning of time, it found something that should not exist: massive galaxies, blazing bright in an era when the cosmos was barely out of its infancy. Black holes that grew impossibly fast, stars and planets forming in ways that break every rule we thought we understood. The James Webb Space Telescope is not just revealing new things about the universe, it is actively undoing our decades-long understanding of reality. Scientists are shocked, some are calling it a crisis, and the more we look, the stranger it gets. You clicked on this video because you wanted to know what James Webb found that has astronomers so worried. And here's the truth. The telescope has uncovered three major conflicts with our best models of how the universe works. First, there are galaxies that appear fully grown when they should still be babies. Second, the universe is expanding at two different speeds, which makes no sense. And third, black holes and planets are showing up in places and at times when they should not exist. These are not small problems. These are fundamental cracks in the foundation of cosmology. So let's take this journey together and explore how a telescope built to answer questions ended up breaking the universe instead. Before we dive into the crisis, we need to understand what makes the James Webb Space Telescope so special. This is not just a bigger version of Hubble. James Webb was designed to see light that has been traveling through space for over 13 billion years. It sees in infrared, which means it can detect the heat signatures of the very first stars and galaxies that formed after the Big Bang. When the universe expands, light stretches. Blue light becomes red light becomes infrared. So if you want to see the earliest moments of cosmic history, you need a telescope that can see infrared light. That is exactly what James Webb does. It is like having thermal goggles that let you see the ghosts of the ancient universe. The telescope launched on Christmas Day in the year 2021. It traveled 1 million miles away from Earth to a special point in space called L2, where it unfurled a massive golden mirror and a sun shield the size of a tennis court. Then it started looking back in time, and almost immediately it started finding things that should not be there. Galaxies that were too big, too bright, too mature. Scientists expected to find faint, small baby galaxies in the first few 100 million years after the Big Bang. Instead, they found cosmic giants. It was like walking into a nursery and finding teenagers. This was the first sign that something was wrong. The James Webb Space Telescope is an engineering marvel. Its primary mirror is 6.5 meters across and made of 18 separate hexagonal segments, each coated in a thin layer of gold. Gold is an excellent reflector of infrared light, which is why the telescope has that distinctive golden appearance. The mirror segments had to be aligned with incredible precision, to within a few billionths of a meter, in order to work as a single coherent mirror. This alignment process took several months after launch and required hundreds of tiny adjustments using actuators on the back of each mirror segment. The fact that this process worked perfectly is itself a minor miracle. The sun shield is equally impressive. It consists of 5 layers of a material called capton, each layer about as thin as a human hair. These layers are separated by gaps that allow heat to radiate away into space. The sun shield keeps the telescope's instruments at a temperature of about -223 degrees Celsius, which is essential for detecting faint infrared signals. If the telescope were warm, its own heat would overwhelm the faint signals from distant galaxies. The sun shield is about the size of a tennis court when fully deployed, making it one of the largest structures ever sent into space. The telescope carries 4 main instruments. The near-infrared camera, or NIRCam, is the primary imaging instrument. It can see light in wavelengths from about 0.6 to 5 microns, which covers the near-infrared spectrum. This is the instrument that has captured many of the stunning images of distant galaxies and nebulae. The near-infrared spectrograph, or NIR spec, breaks light down into its component wavelengths, allowing scientists to determine the chemical composition, temperature, and motion of distant objects. The mid-infrared instrument, or MIRI, extends the wavelength coverage out to 28 microns, allowing the telescope to see cooler objects like dust clouds and distant planets. And the Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph, or FGS-NIRIS, provides both precise pointing control and additional spectroscopic capabilities. Each of these instruments has contributed to the discoveries we are about to explore. NIRCam has been crucial for finding and imaging distant galaxies. NIR spec has been essential for measuring the distances to those galaxies and determining their properties. MIRI has revealed the presence of dust and complex molecules in the early universe. And FGS NIRIS has enabled detailed studies of exoplanet atmospheres. Together, these instruments give the James Webb Space Telescope an unprecedented ability to study the cosmos across a wide range of wavelengths and with extraordinary sensitivity. Now let's talk about the impossible galaxies. This is where the crisis really begins. In the standard model of cosmology, galaxies form slowly. After the Big Bang, the universe was a hot soup of hydrogen and helium gas. Over millions of years, gravity pulled this gas together into clumps. Those clumps grew denser and denser until they ignited into the first stars. Those stars grouped together into the first small galaxies. Then those galaxies merged and grew over billions of years into the massive galaxies we see today. This process takes time, a lot of time. You cannot rush it. Or so we thought. The standard model is based on a theory called lambda cold dark matter, or lambda CDM. Lambda represents dark energy, the mysterious force that is causing the universe's expansion to accelerate. CDM stands for cold dark matter, which is the invisible matter that makes up most of the mass in the universe. According to this model, tiny fluctuations in the density of matter in the early universe caused by quantum effects during a period called inflation grew over time due to gravity. Dark matter clumped together first, creating gravitational wells that attracted normal matter. This normal matter, mostly hydrogen and helium, fell into those wells and eventually formed the first stars and galaxies. The lambda CDM model has been incredibly successful. It explains the pattern of temperature fluctuations in the cosmic microwave background. It explains the large-scale structure of the universe, with galaxies arranged in filaments and clusters separated by vast voids. It explains the abundances of light elements like hydrogen, helium, and lithium that were created in the first few minutes after the Big Bang. It even explains the existence and properties of dark energy. This model has been tested and refined over decades, and it fits the data remarkably well. So when observations started to contradict its predictions, astronomers took notice. When James Webb looked at the universe just a few 100 million years after the Big Bang, it found galaxies that were shockingly massive. One galaxy, nicknamed the Firefly Sparkle, was found at a time when the universe was only 460 million years old. It already had 10 distinct star clusters and a mass similar to what our Milky Way galaxy would have had at that same stage. Another set of galaxies, called the Red Monsters, were discovered within the first billion years after the Big Bang. These galaxies were nearly as massive as the Milky Way is today. They were forming stars at an incredibly fast rate, doubling their stellar mass every 100 million years. For comparison, our Milky Way takes about 25 billion years to double its mass. That is 250 times slower. The problem is not just that these galaxies are big, the problem is that they should not have had enough time to grow this big. According to lambda CDM, the early universe was relatively smooth and uniform. The tiny density fluctuations that seeded galaxy formation were only about 1 part in 100,000. Starting from such small fluctuations, it takes time for gravity to pull matter together. It takes time for the first stars to form. It takes time for those stars to fuse hydrogen into heavier elements. It takes time for those stars to die and explode as supernovae, enriching the surrounding gas with metals. It takes time for new generations of stars to form from that enriched gas. It takes time for galaxies to merge and grow. All of this takes billions of years, not hundreds of millions. Yet here they are, these massive galaxies, shining brightly in an era when they should barely exist. Some scientists have proposed that these early galaxies formed stars much more efficiently than modern galaxies do. Perhaps the gas in the early universe was denser, allowing it to collapse into stars more rapidly. Perhaps the lack of heavy elements in the early universe made it easier for gas to cool and collapse. Perhaps feedback processes like stellar winds and supernova explosions that blow gas out of galaxies and shut down star formation in the modern universe were less effective in the early universe. These are all plausible ideas, and they can partially explain the rapid growth of early galaxies. But even with these adjustments, the models struggle to match the observations. Some of these early galaxies are so massive and so mature that they push the limits of what is possible within the lambda CDM framework. Another possibility is that our estimates of the masses of these galaxies are incorrect. Measuring the mass of a distant galaxy is not straightforward. Astronomers typically use the brightness of a galaxy to estimate its mass, assuming a certain ratio between the mass of stars and the amount of light they produce. This ratio, called the mass-to-light ratio, depends on the ages and types of stars in the galaxy. If the galaxy contains a lot of young, massive, bright stars, the mass-to-light ratio is low. If it contains mostly old, low-mass, dim stars, the mass-to-light ratio is high. Early estimates of the masses of these distant galaxies assumed a certain stellar population, but if that assumption is wrong, the mass estimates could be off. For example, if these galaxies contain an unusually large number of bright, massive stars, they might appear more luminous than typical galaxies of their mass, leading us to overestimate their masses. However, detailed spectroscopic observations by James Webb have confirmed that at least some of these galaxies really are as massive as they appear. The spectroscopy allows astronomers to measure the velocity dispersion of stars in the galaxy, which is directly related to the mass of the galaxy through the virial theorem. These dynamical mass measurements are independent of assumptions about the stellar population, and they confirm that these early galaxies are indeed very massive. So the crisis remains. There is also the question of whether these galaxies are truly at the distances we think they are. The distance to a galaxy is determined by measuring its redshift, which is the amount by which the wavelength of light from the galaxy has been stretched due to the expansion of the universe. The greater the redshift, the farther away the galaxy is, and the earlier in cosmic history we are seeing it. Redshift can be measured spectroscopically by looking for specific spectral lines in the galaxy spectrum and measuring how much they have been shifted to longer wavelengths. It can also be estimated photometrically by measuring the brightness of the galaxy through different filters and comparing those measurements to models of how galaxy spectra look at different redshifts. Spectroscopic redshifts are more accurate, but they require more observing time. Early identifications of distant galaxies by James Webb were based on photometric redshifts, which are quicker but less precise. There was concern that some of these galaxies might not be as distant as initially thought. If their redshifts were overestimated, they would not be as early in cosmic history, and there would be more time for them to grow to their observed sizes. However, follow-up spectroscopic observations have confirmed that many of these galaxies really are at the extreme distances indicated by their photometric redshifts. So while some of the initial candidates turned out to be closer than expected, there are still a significant number of massive galaxies in the very early universe that challenge our models. Now let's move on to the second major crisis, the Hubble tension. This is a problem that has been brewing for years, but James Webb observations have made it worse. The Hubble tension refers to a disagreement about the rate at which the universe is expanding, a value known as the Hubble constant. The Hubble constant tells us how fast galaxies are moving away from us as a function of their distance. It is one of the most important numbers in cosmology because it determines the age and size of the universe. There are two main ways to measure the Hubble constant. The first method uses observations of the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky. The cosmic microwave background was emitted when the universe was only 380,000 years old, and its properties encode information about the conditions in the early universe. By analyzing the pattern of temperature fluctuations in the cosmic microwave background, cosmologists can infer the values of various cosmological parameters, including the Hubble constant. The Planck satellite, which made the most precise measurements of the cosmic microwave background, found a Hubble constant of about 67 kilometers per second per megaparsec. This means that for every megaparsec, or about 3.3 million light-years of distance, galaxies are receding at an additional 67 kilometers per second. The second method uses observations of objects in the nearby universe whose distances and velocities can be measured directly. The most important of these objects are Cepheid variable stars and type Ia supernovae. Cepheid variables are stars that pulsate with a regular period, and the period of pulsation is directly related to the star's intrinsic brightness. By measuring the period, astronomers can determine how bright the star really is. By comparing that to how bright it appears from Earth, they can calculate how far away it is. This makes Cepheids excellent distance indicators. Type Ia supernovae are even brighter and can be seen at much greater distances. They occur when a white dwarf star in a binary system accretes matter from its companion until it reaches a critical mass and explodes. Because all type Ia supernovae reach roughly the same peak brightness, they serve as standard candles. By measuring how bright they appear, astronomers can determine their distances. Using Cepheids and type Ia supernovae, astronomers can build a cosmic distance ladder, calibrating distances to increasingly distant objects. By combining these distance measurements with measurements of how fast the objects are moving away from us, obtained from their redshifts, astronomers can determine the Hubble constant. The Shell 0ES team, led by Adam Rees, has made the most precise measurements using this method. They find a Hubble constant of about 73 kilometers per second per megaparsec. So we have two different measurements of the same number and they disagree. 67 versus 73. That might not sound like a big difference, but in science, a difference this large is significant. The two measurements differ by about 9%, and both measurements are very precise, with uncertainties of only a few percent. This means the difference is real and cannot be explained by measurement error. One of the two measurements, or both, must be wrong. Or more intriguingly, there might be new physics at play that causes the discrepancy. The Hubble tension has been studied intensely for years, and every attempt to resolve it has failed. Systematic errors in the measurements have been checked and rechecked. Different methods of measuring distances have been used. Different datasets have been analyzed. The tension remains, and now James Webb has made it worse. One of the hopes was that James Webb would help resolve the Hubble tension by providing more accurate measurements of Cepheid variable stars. Because James Webb observes in the infrared, it is less affected by dust than visible light telescopes like Hubble. Dust in space scatters and absorbs visible light, making objects appear dimmer and redder than they really are. This can introduce errors in distance measurements. Infrared light passes through dust more easily, so James Webb should be able to make more accurate measurements of Cepheids and other distance indicators. However, when the Shell 0ES team used James Webb to observe Cepheids, they found that the Hubble constant was still about 73 kilometers per second per megaparsec. The more precise infrared observations did not bring the value closer to the cosmic microwave background value. If anything, they made the discrepancy more certain. The Hubble tension is now more firmly established than ever. So what could be causing the Hubble tension? There are several possibilities. One is that there is a subtle error in one of the measurement methods that has not been identified yet. Maybe there is something we do not understand about Cepheid variable stars or type Ia supernovae. Maybe there is some unknown effect that is biasing the distance measurements. Maybe the analysis of the cosmic microwave background data is missing some subtle effect. These are all possibilities, but after years of scrutiny, most astronomers are skeptical that a simple error explains the discrepancy. Another possibility is that the lambda CDM model itself is incomplete. The model assumes that the universe is homogeneous and isotropic, meaning it looks the same in all directions and at all locations on large scales. It assumes that dark energy has a constant density over time, a property characterized by an equation of state parameter WW equal to -1. It assumes that general relativity correctly describes gravity on cosmological scales. If any of these assumptions is wrong, it could affect the Hubble constant measurements. For example, if dark energy is not constant, but instead evolves over time, the expansion rate of the universe could be different in the early universe compared to today. This could cause a discrepancy between the Hubble constant inferred from the cosmic microwave background, which probes the early universe, and the Hubble constant measured from nearby objects, which probes the recent universe. This idea is called early dark energy, and it has been explored in many theoretical models. However, early dark energy models face their own challenges and have not yet provided a fully satisfactory explanation for the Hubble tension. Another possibility is that there is an unknown component of the universe that affects its expansion history. This could be a new particle, a new field, or some other exotic form of matter or energy. Such a component would need to have very specific properties to explain the Hubble tension without conflicting with other observations. Some proposals include decaying dark matter, interacting dark energy, or modifications to general relativity. All of these ideas are speculative and require more evidence. There is also the possibility that the discrepancy is telling us something fundamental about the nature of the universe. Perhaps the universe is not as homogeneous as we think. Perhaps there are large-scale structures or voids that affect the local expansion rate. Perhaps we live in a region where the expansion rate is different from the average. This idea, called a local void, has been explored, but observations suggest that any such void would have to be extremely large, much larger than what we typically see in the cosmic web of galaxies. And even then, it might not fully explain the Hubble tension. The Hubble tension remains one of the most pressing problems in cosmology, and James Webb observations have not resolved it. If anything, they have made it more acute. The fact that two independent methods give such different results suggests that we are missing something important. The third major crisis involves black holes and planets. James Webb has found supermassive black holes in the early universe that are far too big for their age, and it has found planets forming in environments where they should not be able to form. Let's start with the black holes. Supermassive black holes are monsters. They can have masses of millions or even billions of times the mass of the Sun. They sit at the centers of most large galaxies, including our own Milky Way. The black hole at the center of the Milky Way, called Sagittarius A star, has a mass of about 4 million solar masses. The largest known black holes have masses of tens of billions of solar masses. We know that supermassive black holes exist in the centers of galaxies, but we do not fully understand how they formed. There are two main theories. The first is that they grew from stellar mass black holes. When a massive star dies, it can collapse into a black hole with a mass of a few to a few tens of solar masses. This black hole can then grow by accreting gas and merging with other black holes over billions of years. Through many cycles of accretion and mergers, a stellar mass black hole could grow into a supermassive black hole. The problem with this scenario is that it takes time. There is a limit to how fast a black hole can grow by accretion, called the Eddington limit. When a black hole accretes matter, the infalling matter heats up and emits radiation. This radiation exerts an outward pressure that counteracts the inward pull of gravity. If the accretion rate is too high, the radiation pressure becomes so strong that it blows away the infalling matter, shutting down the accretion. The Eddington limit sets the maximum rate at which a black hole can grow. For a black hole starting at 10 solar masses and growing at the Eddington limit, it would take about 1 billion years to reach 1 billion solar masses. But James Webb has found supermassive black holes that existed when the universe was less than 1 billion years old. Some of these black holes have masses of hundreds of millions or even billions of solar masses. There simply has not been enough time for them to grow from stellar mass seeds, even if they were accreting at the Eddington limit the entire time. This suggests that these black holes must have started much larger. The second theory is that supermassive black holes form from the direct collapse of massive gas clouds in the early universe. Instead of forming from a star, a large cloud of gas could collapse directly into a black hole with a mass of thousands or even hundreds of thousands of solar masses. Such a black hole could then grow to supermassive sizes much more quickly. This is called the direct collapse black hole scenario. For a gas cloud to collapse directly into a black hole, it needs to be very massive and it needs to avoid fragmenting into stars. This requires special conditions. The gas needs to be relatively free of heavy elements because heavy elements cool the gas and allow it to fragment. The gas also needs to be heated by some external source, such as intense ultraviolet radiation from nearby stars or galaxies, to prevent it from cooling and fragmenting. These conditions might have been more common in the early universe, before there were many heavy elements and when there were intense sources of radiation. However, even with direct collapse black holes, there are challenges. The conditions required for direct collapse are quite specific, and it is not clear how common they were. And even direct collapse black holes would need to grow significantly to reach the masses of the supermassive black holes observed by James Webb. James Webb observations suggest that supermassive black holes were more common in the early universe than expected. They also appear to be growing faster than models predict. Some of these black holes are accreting at rates that exceed the Eddington limit, a phenomenon called super-Eddington accretion. Super Eddington accretion can occur under certain conditions, such as when the accretion flow is not spherically symmetric or when magnetic fields play a role, but it is not fully understood. The fact that these black holes exist and are growing so rapidly in the early universe is another challenge too. Our models. Now let's talk about planets. Planets form in disks of gas and dust that surround young stars. The gas and dust in the disk gradually clump together through collisions and gravitational attraction, forming larger and larger bodies. First, dust grains stick together to form pebbles. Pebbles collide to form rocks. Rocks collide to form planetesimals. Planetesimals collide to form protoplanets, and protoplanets collide to form planets. This process takes millions of years and requires a stable disk of material. The disk itself forms from the collapse of a molecular cloud. When a star forms, not all of the material in the cloud falls onto the star. Some of it forms a rotating disk around the star. This disk is where planets form. In the standard model of planet formation, planets form after the star has finished most of its growth and the disk has settled into a relatively stable configuration. But James Webb has found planets forming around stars that are still in their infancy, in environments that should be too chaotic and violent for planets to form. One of the most surprising discoveries involves planets forming in a region called the Orion Nebula Cluster. This is a dense cluster of young stars, many of which are massive and emit intense ultraviolet radiation. This radiation should heat up and evaporate the disks around smaller stars, preventing planets from forming. Yet James Webb has found evidence of planet-forming disks around stars in this harsh environment. This suggests that planet formation can occur even in conditions that we thought were too hostile. Another surprising discovery involves planets around brown dwarfs. Brown dwarfs are objects that are too massive to be called planets, but not massive enough to sustain hydrogen fusion like stars. They are sometimes called failed stars because brown dwarfs are so small and dim, it was thought that they would not have enough material in their disks to form planets. But James Webb has found disks around brown dwarfs that appear to be forming planets. This expands the range of environments where planets can form and suggests that planet formation is more robust and widespread than we thought. These discoveries are forcing astronomers to rethink the conditions necessary for planet formation. It appears that planets can form in a wider variety of environments and at earlier stages of stellar evolution than previously believed. This has implications for the prevalence of planets in the universe and the potential for life. If planets can form in more environments, there may be more planets out there than we thought. And more planets means more potential homes for life. So we have three major crises: galaxies that are too big too soon, a universe that is expanding at two different rates, and black holes and planets that should not exist. These are not minor discrepancies. These are fundamental challenges to our understanding of the cosmos, and they all stem from observations made by a single telescope. The James Webb Space Telescope was supposed to answer questions. Instead, it has raised new ones. It has revealed a universe that is stranger and more complex than we imagined, and that is both humbling and exciting, because it means we still have so much to learn. The James Webb Space Telescope is still in its early years of operation. It has already made groundbreaking discoveries, but there are many more to come. As the telescope continues to observe the universe, it will gather more data on distant galaxies, black holes, exoplanets, and other phenomena. Each new observation has the potential to deepen the mysteries or provide clues to their solutions. One of the key areas of ongoing research is the study of the first stars, sometimes called population 3 stars. These stars form from the primordial gas left over from the Big Bang, which consisted almost entirely of hydrogen and helium. Unlike modern stars, which contain heavy elements like carbon, oxygen, and iron, population 3 stars were metal-free. This made them very different from stars we see today. They were likely much more massive, much hotter, and much shorter-lived. When they died, they exploded as supernovae, enriching the surrounding gas with the first heavy elements and paving the way for subsequent generations of stars. Population 3 stars have never been directly observed. They existed so long ago and were so distant that even the James Webb Space Telescope may not be able to see individual population 3 stars. However, the telescope might be able to detect their signatures in other ways. For example, the supernovae of population 3 stars might be visible as brief, bright flashes, or the chemical fingerprints of population 3 stars might be detectable in the spectra of early galaxies. Another indirect way to study population 3 stars is through their effect on the cosmic microwave background. During the era of reionization, the first stars and galaxies ionized the hydrogen in the universe, turning it from neutral to ionized. This process affected the cosmic microwave background by scattering some of its photons. By studying the polarization of the cosmic microwave background, astronomers can learn about the timing and nature of reionization, which in turn tells us about the first stars. James Webb observations of high redshift galaxies are providing new insights into reionization. By measuring the amount of neutral hydrogen in and around these galaxies, astronomers can map out how reionization proceeded. Early results suggest that reionization was a patchy process, with some regions of the universe ionizing earlier than others. This is consistent with models in which the first galaxies formed in overdense regions and gradually ionized their surroundings. The study of reionization is closely connected to the study of the intergalactic medium, the gas that fills the space between galaxies. Before reionization, the intergalactic medium was cold and neutral. After reionization, it was hot and ionized. The properties of the intergalactic medium affect how light from distant objects travels through the universe, and they provide clues about the history of star formation and black hole growth. James Webb is also contributing to our understanding of the epoch of reionization by detecting Lyman alpha emission from distant galaxies. Lyman alpha is a specific wavelength of light emitted by hydrogen when an electron transitions from the second energy level to the first. In the neutral universe before reionization, Lyman alpha photons would have been scattered and absorbed by neutral hydrogen, making it difficult to detect Lyman alpha emission from distant galaxies. But as reionization progressed and the universe became more ionized, Lyman alpha photons could travel more freely. By measuring the Lyman alpha emission from galaxies at different distances corresponding to different times in cosmic history, astronomers can trace the progress of reionization. The James Webb Space Telescope has detected Lyman alpha emission from some of the most distant galaxies known, providing evidence that these galaxies were surrounded by ionized bubbles of gas. Another key question is how the intergalactic medium, the gas that fills the space between galaxies, was affected by reionization. Before reionization, the intergalactic medium was cold and neutral. After reionization, it was hot and ionized. But the transition was not instantaneous or uniform. Reionization occurred in a patchy, inhomogeneous way, with some regions ionizing earlier than others. The exact topology of reionization, the sizes and shapes of the ionized bubbles, depends on the distribution of the ionizing sources and the density structure of the intergalactic medium. James Webb observations of the Lyman alpha forest, a series of absorption lines in the spectra of distant quasars caused by neutral hydrogen, are providing new constraints on the topology of reionization and the properties of the intergalactic medium. The era after reionization, from about 1 billion years after the Big Bang to the present day, is called the era of galaxy assembly. This is when galaxies grew through mergers, accretion, and star formation to become the massive systems we see today. It is also when the cosmic star formation rate reached its peak, around 2 to 3 billion years after the Big Bang, in an epoch sometimes called cosmic noon. During cosmic noon, galaxies were forming stars at rates 10 to 100 times higher than galaxies today. The universe was a much more active and energetic place. James Webb is providing new insights into cosmic noon as well. By observing galaxies at redshifts of 2 to 3, corresponding to cosmic noon, astronomers can study the processes that drove the peak of star formation in the universe. They can measure the gas content of these galaxies, the efficiency with which they converted gas into stars, and the role of mergers and interactions in triggering star formation. They can also study the buildup of heavy elements in these galaxies and how those elements were distributed through stellar winds and supernova explosions. These observations are helping to build a complete picture of galaxy evolution from cosmic dawn to the present day. One of the surprising findings from James Webb is that even at cosmic noon, galaxies were more diverse and complex than expected. Some galaxies were compact and dense, forming stars at prodigious rates in their central regions. Others were extended and diffuse, with star formations spread out over large areas. Some galaxies showed clear signs of recent mergers, with disturbed morphologies and tidal tails. Others appeared relatively undisturbed, growing through the steady accretion of gas from the cosmic web. This diversity suggests that there is no single pathway for galaxy evolution. Different galaxies followed different evolutionary tracks depending on their environment, their merger history, and the properties of their dark matter halos. The chemical evolution of galaxies is another area where James Webb is making important contributions. Chemical evolution refers to the process by which heavy elements, or metals in astronomical terminology, are created in stars and distributed through galaxies and the intergalactic medium. The first stars in the universe were made of pure hydrogen and helium, the elements created in the Big Bang. But when those stars died, they released heavier elements into their surroundings through stellar winds and supernova explosions. Subsequent generations of stars incorporated these heavy elements, and when they died, they enriched the environment even further. Over billions of years, this process gradually increased the metallicity of galaxies and the intergalactic medium. James Webb can measure the metallicity of distant galaxies by analyzing their spectra. Different elements produce different emission and absorption lines at specific wavelengths, and the strength of these lines is related to the abundance of the elements. By measuring the abundances of oxygen, carbon, nitrogen, and other elements, astronomers can infer the metallicity of a galaxy and compare it to theoretical models of chemical evolution. Early results from James Webb show that some galaxies in the early universe already had surprisingly high metallicities, indicating that they had experienced rapid enrichment from multiple generations of stars. This is consistent with the picture of efficient star formation in early galaxies that we discussed earlier. The distribution of metals within galaxies is also important. In the local universe, there are gradients in metallicity, with the central regions of galaxies being more metal-rich than the outskirts. These gradients are thought to arise from the inside-out growth of galaxies, with the central regions forming stars earlier and more rapidly than the outer regions. But in the early universe, the metallicity gradients might have been different, depending on how gas and metals were transported within galaxies. James Webb observations are beginning to reveal the metallicity structure of distant galaxies, providing clues about the processes that shape chemical evolution. So as we wrap up this journey through the shocking discoveries of the James Webb Space Telescope, remember this. The James Webb Space Telescope did not break the universe. It broke our models. It broke our assumptions. It broke our complacency. And that is a good thing, because now we have the chance to build something better, something truer, something closer to the reality of the cosmos. And that is the most exciting part of all. The universe is speaking to us through the light gathered by the James Webb Space Telescope. It is telling us stories of ancient stars and newborn galaxies. It is whispering secrets about black holes and dark energy. It is revealing the intricate dance of matter and energy that has been playing out for nearly 14 billion years. And we are here in this moment with the privilege and the responsibility to listen, to learn, to understand, and to pass that knowledge on to future generations. The discoveries are just beginning. The mysteries are just unfolding, and the adventure is far from over. Thank you for joining me on this journey through the shocking discoveries of the James Webb Space Telescope. I hope you found it as fascinating as I did. If you enjoyed this deep dive into the mysteries of the cosmos, please consider liking this video and subscribing to the channel for more content like this. And I would love to hear your thoughts. What do you think is the most shocking discovery made by James Webb? Do you think we will solve the Hubble tension in our lifetime? What do you think the little red dots really are? Drop a comment below and let's discuss. Until next time, keep looking up. Keep wondering and keep exploring. The universe is out there, waiting to be discovered. And who knows, maybe one day you will be the one to unlock its secrets.